Look up. There is a shape in the night sky you have known since before you knew your own name. The moon. Pale, familiar, patient. You learned to point at it from a car seat. You have seen it rise over cities and oceans, through airplane windows and bedroom curtains. It feels permanent. It feels peaceful. It feels like it has always been there, watching over the earth the way a parent watches over a sleeping child. But what if I told you that the quiet face in the sky is a scar? Those craters are not decorations. They are wounds, each one a record of something slamming into the surface at 20,000 kilometers per hour. The dark patches you see, the ones that form what some cultures call the man in the moon, are not shadows. They are ancient seas of frozen lava, places where the moon bled from the inside after being struck by asteroids the size of cities. And the moon itself, the whole of it, is the debris of a collision so violent it nearly erased the Earth from existence. 4.5 billion years ago, a planet the size of Mars came out of the dark and hit us. The impact did not leave a crater. It vaporized rock. It peeled away the crust of the young Earth like skin from a fruit. It sprayed molten debris into orbit, a fountain of liquid stone arcing into the void. The temperatures at the point of collision exceeded 10,000 degrees, hotter than the surface of the sun. For a few terrible hours, there was no Earth as we would recognize it. There was only a spinning cloud of plasma and fire, two worlds merged into one screaming mass of chaos. And from that chaos, over hours or perhaps days, the moon assembled itself. That is what hangs in your window tonight. Not a guardian, not a gentle lantern, a tombstone, a graveyard orbiting the scene of the crime. The largest scar in the solar system, born from the death of a world we never knew existed. The planet that struck us has a name. Scientists call it Theia, after the Greek titan who gave birth to Selene, the goddess of the moon. It is a fitting name. In mythology, Theia was a deity of sight and the shining light of the clear blue sky. In reality, she was a world unto herself, with her own iron core, her own rocky mantle, perhaps her own thin atmosphere. She had been growing in the shadows of the young solar system for millions of years, hidden in a gravitational pocket where the pull of the sun and the pull of Earth cancelled each other out. She was not a rogue asteroid tumbling through space. She was a neighbor, a sister even. And then, one day, her orbit became unstable and gravity turned her into a weapon. We will never find a fragment of Theia drifting through the asteroid belt. We will never locate her remains among the meteorites that fall to Earth. She was destroyed so completely, mixed so thoroughly with the molten material of the young Earth, that almost nothing of her original form survived. Almost nothing. Because scientists have recently discovered that pieces of Theia may still exist, not in space, not on the moon, but deep beneath your feet, buried at the boundary between Earth's mantle and its core, two continent-sized masses of alien rock that have been hiding there for 4.5 billion years. The moon is not just orbiting the Earth, it is orbiting the grave of its mother. There are numbers that help us grasp the scale of what happened, though numbers can only take us so far. The energy released in the collision was equivalent to detonating every nuclear weapon ever built, 10 billion times over. The debris ejected into orbit weighed approximately 70 billion trillion kilograms. The moon that formed from this debris was so close to Earth that if you could have stood on the molten surface and looked up, it would have filled a quarter of the sky, a massive red orb glowing with its own heat, close enough that you could have driven there in 10 days if the road existed. Today, that same drive would take 5 months. The moon is still moving away from us. Every year, it drifts 3.8 centimeters farther into space, roughly the speed at which your fingernails grow. This is not a metaphor. This is a measurable fact, confirmed by bouncing laser beams off mirrors that Apollo astronauts left on the lunar surface more than 50 years ago. The Moon is leaving, slowly, imperceptibly, and in 600 million years it will be too far away to completely cover the Sun during an eclipse. The perfect alignment that allows us to witness the solar corona, that ring of ghostly white fire that appears when the Moon blocks the Sun's bright face, is a temporary gift. We are living in a window of time, perhaps 100 million years wide, when the Moon and Sun appear almost exactly the same size in our sky. This is a coincidence. There is no physical law that requires it. The Sun is 400 times larger than the Moon, but it is also 400 times farther away. The math just happens to work out. The universe does not owe us such gifts, but here we are, on a planet that exists because another planet died, watching eclipses that will not last forever, under a moon that carries in its grey dust the memory of the day that made us. If you enjoy this kind of slow, quiet exploration, I would be grateful if you subscribed. Let me know in the comments where you are listening from and what time it is there. I am curious about the places where these stories travel. Tonight, we go back to the beginning. We will meet Theia, the planet that killed us and created us in the same moment. We will stand on the surface of the young Earth and watch as a second sun rises in the east, a sun that is not a sun, a world falling toward us at 10 kilometers per second. We will witness the collision, the magma oceans, the slow cooling, the bombardment that followed. We will learn why the Moon shows the same face to Earth every night, why its far side looks so different from the side we see, and why scientists believe it may have played a crucial role in making Earth habitable for life. And we will discover that Theia never truly left. She is still here, above us in the night sky, and below us in the deep earth. The story begins 4.5 billion years ago in a solar system that looked nothing like the one we know, a place of fire and collision and worlds being born. The Sun was young once. It is difficult to imagine now, looking at that steady yellow disk that rises each morning with such predictable calm. But there was a time when our star had just ignited, when the nuclear fires at its core had only recently begun to burn. 4.6 billion years ago, give or take a few million, the Sun opened its eyes for the first time and found itself surrounded by chaos. What we now call the solar system was not a system at all. It was a disk, a vast, swirling cloud of gas and dust and ice, spinning around the newborn star like water circling a drain. This disk stretched for billions of kilometers, thin at the edges and thick near the center, and it contained everything that would eventually become the planets, the moons, the asteroids, the comets. All of it was there, but none of it had form. The ingredients existed. The recipe had not yet been followed. The dust grains were impossibly small, smaller than the width of a human hair. They drifted through the disk like smoke, colliding with one another, sometimes bouncing apart, sometimes sticking together. When they stuck, they grew. A grain became a pebble became a stone became a boulder, and a boulder, given enough time and enough collisions, became something larger still. Scientists call these early objects planetesimals, a word that means almost planets, and they ranged in size from a few meters to a few hundred kilometers across. They were the building blocks of worlds. The process was not gentle. Every collision released energy. Every impact generated heat. The planetesimals that grew largest did so by consuming their smaller neighbors, pulling them in with gravity and absorbing them in violent mergers that melted rock and vaporized ice. The young solar system was not a peaceful nursery. It was an arena, and only the largest competitors would survive. Earth began as one of these competitors. Not Earth as we know it, with blue oceans and green continents, but a molten sphere of rock and metal, glowing red and orange against the black of space. Scientists call this early version of our planet the Proto-Earth, a term that acknowledges how different it was from the world we inhabit today. The Proto-Earth had no atmosphere, or if it did, it was a thin envelope of hydrogen and helium that would soon be stripped away by the solar wind. It had no water on its surface, only magma, liquid rock heated to temperatures that would vaporize steel. It had no magnetic field to protect it from radiation. It was, in every meaningful sense, uninhabitable, a world of fire still in the process of becoming. The Proto-Earth was not alone in its orbit. The region of space where our planet formed, roughly 150 million kilometers from the Sun, was crowded with debris. Millions of planetesimals shared this orbital zone, and they collided constantly. Some of these collisions were glancing blows that sent both objects spinning away in new directions. Others were direct hits that shattered one or both bodies into fragments. And some, the most significant ones, were mergers, events where two large objects combined to form something even larger. The Proto-Earth grew through these mergers, absorbing the mass and momentum of everything it encountered. But there was another object growing in the same region of space, another proto-planet, accumulating mass, pulling in debris, competing for the same orbital territory. This object would eventually be named Theia, though of course no one existed to name it at the time. Theia was smaller than the Proto-Earth, perhaps the size of Mars, but she was not small. She had her own iron core, dense and hot, sinking toward her center as lighter materials floated upward. She had her own mantle, a thick layer of silicate rock surrounding the core. She may have had her own crust, though it would have been thin and unstable, constantly recycled by volcanic activity. Theia was a world in progress, and in a different version of history, she might have continued growing until she became a full-fledged planet. The question that puzzled scientists for decades was simple: where was Theia hiding? If she was as large as Mars and orbiting in the same region as Earth, why did the two objects not collide sooner? Why did Theia have millions of years to grow before the fatal encounter? The answer lies in one of the strangest features of orbital mechanics, a set of locations in space where gravity plays tricks with moving objects. In any system where two large bodies orbit each other, there are 5 points where the gravitational forces balance in peculiar ways. These are called Lagrange points, named after the mathematician who first calculated their positions. 3 of them are unstable, places where an object will drift away if given the slightest push, but 2 of them, known as L4 and L5, are stable. An object placed at L4 or L5 will tend to stay there, trapped in a gravitational eddy, orbiting the Sun at the same distance as the larger body, but always 60 degrees ahead or 60 degrees behind. Theia, according to the most widely accepted models, spent her formative years at one of these Lagrange points. She was not chasing Earth or fleeing from it. She was locked in step with our planet, sharing the same orbit but separated by a fixed angle, invisible in the sense that she never drew close enough to interact directly. For tens of millions of years, Theia grew in this gravitational harbor, accumulating mass from the debris that drifted into her vicinity, completely undetected by the Proto-Earth that would eventually destroy her. The problem with Lagrange points is that they are only stable up to a limit. An object can remain at L4 or L5 indefinitely, but only if it stays below a certain mass. For the Earth-Sun system, that threshold is approximately 10% of Earth's mass, which happens to be roughly the mass of Mars. When Theia crossed this threshold, her presence began to disturb the gravitational balance that had kept her hidden. Small perturbations from passing planetesimals, tugs from Jupiter's immense gravity, subtle shifts in the distribution of mass throughout the inner solar system. All of these factors conspired to nudge Theia out of her stable orbit. The departure was slow at first. Theia drifted a few thousand kilometers from her equilibrium position, then a few tens of thousands, then more. Each deviation made the next one larger. The gravitational forces that had once held her in place now pushed her further away, and she began to swing through the inner solar system on an increasingly erratic path. Sometimes she passed close to the proto-Earth, close enough that the two objects could see each other as bright points of light in their respective skies. Sometimes she swung out toward Mars or in toward Venus, her orbit becoming more elliptical with each close encounter. This could not continue indefinitely. Orbital mechanics has a way of resolving unstable situations, usually through collision or ejection. Theia was not moving fast enough to escape the inner solar system entirely, which meant that sooner or later she would intersect the path of another large body. The most likely candidate was the proto-Earth, the object whose gravity had destabilized her orbit in the first place. We do not know exactly how long this chaotic phase lasted. Computer simulations suggest it could have been as short as a few million years, or as long as 100 million. We do not know how many close calls occurred, how many times Theia swept past Earth at distances that would have made the encounter spectacular but not catastrophic. What we do know is that approximately 4.5 billion years ago, between 20 and 100 million years after the Sun first ignited, the geometry finally aligned. Theia was falling toward Earth. Not directly, not head-on, but at an angle, a glancing trajectory that would bring the two worlds into contact along their edges rather than their centers. The approach speed was approximately 10 kilometers per second, fast enough to cross the distance from New York to Los Angeles in 6 minutes. At this velocity, neither gravity nor human intervention could have altered the outcome. The collision was inevitable. On the surface of the proto-Earth, if anyone had been there to witness it, the signs would have appeared slowly at first. A new light in the sky, dim and reddish, growing brighter over the course of weeks. The color would shift as Theia drew closer, from the dull red of a cooling ember to the angry orange of molten metal. By the final hours, Theia would have been larger than the Moon appears today, a massive disk of glowing rock filling a significant portion of the sky. There would have been no sound, no warning rumble, because sound requires air and the proto-Earth had almost none. Just that silent, swelling presence, a second world rising in the east. And then contact. The first moment of contact lasted less than a second. Theia's leading edge, a curved wall of semi-molten rock traveling at 10 kilometers per second, touched the surface of the proto-Earth somewhere near what we might loosely call the equator. At that velocity, rock does not behave like rock. It does not crack or shatter or crumble. It behaves like liquid. The atoms at the point of impact had no time to transmit force to their neighbors, no time to distribute the energy of collision through the crystal structure of the minerals. They simply vaporized, transformed instantly from solid matter into a plasma hotter than the surface of the sun. The energy released in that first second exceeded the total energy output of human civilization across all of recorded history. And it was only the beginning. What followed was not an explosion in the conventional sense. Explosions push outward from a central point, spherical and symmetric. This was something else entirely. The collision was oblique. A glancing blow struck at an angle of approximately 45 degrees, and the geometry of impact created forces that twisted and sheared the two worlds rather than simply blasting them apart. Theia did not bounce off the proto-Earth. She plowed into it, her momentum carrying her forward even as the resistance of Earth's mass began to slow her down. For several minutes that must have seemed like hours, The two planets occupied the same space, their mantles interpenetrating, their cores drawing toward each other like drops of mercury on a tilted surface. The temperatures at the collision interface exceeded 10,000 degrees Celsius. At such temperatures, rock does not merely melt, it ionizes. Electrons are stripped from their atoms, creating a soup of charged particles that glows with its own fierce light. The color of this light would have been predominantly white, shading to blue at the hottest points, though no human eye could have survived long enough to perceive it. The brightness would have exceeded that of the sun by several orders of magnitude. If there had been any solid surface left to stand on, the radiant heat alone would have vaporized an observer from 1,000 kilometers away. The proto-Earth began to deform. Its spherical shape, maintained by the balance between gravity pulling inward and internal pressure pushing outward, could not withstand the asymmetric forces of the impact. The side struck by Theia bulged inward, compressed by the collision, while the opposite side bulged outward, stretched by the momentum transfer. The planet became elongated, then pear-shaped, then something that no longer resembled a planet at all. Within the first hour, the proto-Earth had lost any coherent structure. It had become a spinning cloud of vaporized rock and liquid magma, a structure that scientists call a synestia, though that term would not be invented for another 4.5 billion years. Theia fared even worse. Her smaller mass meant that she absorbed a disproportionate share of the collision energy. Her mantle was stripped away almost entirely, peeled off in sheets and sprays of molten rock that fountained into space. Her iron core, denser and more cohesive, held together longer, but even it could not survive intact. The core deformed, elongated, broke into fragments. The largest of these fragments spiraled inward toward the center of mass of the combined system, eventually merging with the proto-Earth's own core. This is why Earth has such a large iron core relative to its size, larger proportionally than any other rocky planet in our solar system. We inherited Theia's heart. The debris that did not fall back toward the center was flung outward into space, not gently, not in an orderly fashion, but violently, in jets and streams and spiraling arcs of incandescent matter. The trajectories of these fragments were determined by their velocity at the moment of ejection and by the gravitational pull of the combined Earth-Theia mass. Some fragments achieved escape velocity and departed the Earth-Moon system entirely, destined to orbit the Sun as independent objects or to be swept up later by other planets. But most did not escape. Most remained bound to the system, trapped in orbits that ranged from nearly circular to wildly elliptical, forming a disk of debris that encircled the ruined Earth like a ring of fire. This disk was not like the rings of Saturn. Saturn's rings are made of ice and rock, cold and ancient, spread thin across hundreds of thousands of kilometers. The disk that surrounded Earth after the Theia impact was made of vapor and magma, blindingly hot, concentrated in a thick torus that extended perhaps 50,000 kilometers from the planet's center. The material in this disk was moving fast, orbiting the Earth in hours rather than days, colliding and merging and fragmenting in a constant churn of activity. The disk glowed with its own light, bright enough that it would have been visible from neighboring planets if anyone had been there to look. Within this chaos, something remarkable began to happen. The fragments in the disk were not distributed evenly. Random variations in density, the echoes of turbulence in the original collision, meant that some regions contained slightly more mass than others. These denser regions exerted slightly stronger gravitational pulls on their surroundings, drawing in nearby material and growing larger. As they grew, their gravitational influence increased, allowing them to draw in even more material. This is the same process that built the planets from the original solar nebula, but it happened much faster here because the disk was so dense and so hot. The traditional model of lunar formation, developed in the decades after the Apollo missions, suggested that this accumulation process took months or even years. Small moonlets formed first, then collided and merged to create larger moonlets, which in turn combined to form the moon we know today. This gradual assembly explained certain features of the moon, including its relatively low iron content and its lack of volatile elements, substances that would have boiled away during the extended period of high temperatures. But recent simulations have challenged this picture. In 2022, researchers at NASA's Ames Research Center and Durham University in the United Kingdom published a series of high-resolution computer models that suggested a far more dramatic scenario. According to their calculations, the moon may have formed almost instantaneously, coalescing from the debris disk in a matter of hours rather than months. The key insight was that the collision ejected material not just as a diffuse spray, but as coherent streams, jets of matter that maintained their integrity long enough to gravitationally collapse into a single large body. If this model is correct, then the moon was not assembled piece by piece like a puzzle. It was born whole, pulled together by gravity in a single catastrophic act of creation. Whether the formation took hours or years, the end result was the same. A new world hung in the sky above the ruined Earth, a world made from the mixed remains of two planets that had ceased to exist. The moon was not captured from elsewhere in the solar system. It was not spun off from a rapidly rotating Earth. It was not formed alongside Earth from the same primordial material. It was forged in fire, born from violence, assembled from the debris of a collision that remade the inner solar system. The young moon was nothing like the grey, cratered sphere we see today. It was incandescent, glowing red and orange with its own internal heat. Its surface was not solid rock but liquid magma, a global ocean of molten stone that would take millions of years to cool and solidify. It hung close to the Earth, perhaps only 24,000 kilometers away, compared to the 384,000 kilometers that separate us today. At that distance, the moon would have appeared roughly 15 times larger in the sky than it does now. It would have dominated the heavens, a massive red disk that never set, that hung always in the same position relative to the Earth's surface, because the two bodies were already beginning to synchronize their rotations. The Earth itself was scarcely more hospitable. The collision had liquefied the planet's outer layers to a depth of hundreds of kilometers, creating a magma ocean that covered the entire globe. There was no solid ground anywhere, no continents, no seafloor, nothing but churning liquid rock beneath an atmosphere of vaporized silicates and metal. The sky, if it could be called a sky, was not blue or black, but orange, thick with suspended particles that scattered light in all directions. The temperature at the surface exceeded 2,000 degrees Celsius. The pressure was immense, tens or hundreds of times greater than Earth's current atmospheric pressure, because so much material had been vaporized by the impact. This was the Hadean Aeon, named after Hades, the Greek god of the underworld. It is an appropriate name. The early Earth was a vision of hell, a world of fire and poison and crushing heat, utterly hostile to anything we would recognize as life. The Hadean would last for approximately 500 million years, during which the Earth would slowly cool. The magma ocean would solidify, the atmosphere would condense, and the first liquid water would begin to accumulate on the surface. But all of that lay in the future. In the immediate aftermath of the Theia collision, the Earth was not a planet. It was a furnace. And yet, this furnace would eventually become home. The violence that created the moon also set in motion processes that would make Earth habitable. The collision delivered angular momentum that would stabilize Earth's rotation. The iron from Theia's core sank to Earth's center, strengthening the magnetic field that would one day protect the surface from solar radiation. The impact may have stripped away Earth's original atmosphere, allowing a new atmosphere to form from volcanic outgassing, an atmosphere that would eventually contain the oxygen we breathe. Even the Moon itself, that tombstone orbiting the scene of destruction, would play a role in making Earth suitable for life, stabilizing the planet's axial tilt and driving the tides that may have been crucial to the origin of living organisms. The catastrophe was also a creation. The death of two worlds was the birth of one. Theia was gone, but she had not vanished without a trace. She lived on in the iron core beneath our feet, in the grey regolith of the lunar surface, in the very fact of our existence. Without the collision, there would be no Moon. Without the Moon, the Earth might wobble chaotically on its axis, subjecting the surface to climate swings that would make complex life impossible. Without the collision, Earth's core might be smaller, its magnetic field weaker, its surface bombarded by radiation that would sterilize any organism that dared to emerge. We are here because Theia died. We are, in a very real sense, the children of that ancient violence. The fires cooled, the magma ocean began to solidify, and then, for the first time in 100 million years, something strange happened in the space between Earth and Moon. It began to rain. Rain is not the right word, but there is no right word for what happened next. The English language evolved to describe phenomena on a temperate planet with liquid water and breathable air. It has no vocabulary for the condensation of vaporized rock from a superheated atmosphere onto a surface of molten magma. So we borrow the word rain and ask it to carry a meaning it was never designed to hold. In the millennia following the collision, the Earth existed in a state that defied simple description. The surface was liquid, a global ocean of magma that ranged in temperature from 1200 degrees Celsius at the coolest points to over 2000 degrees, where volcanic upwelling brought fresh material from below. Above this ocean hung an atmosphere unlike anything in our experience, a thick envelope of silicon monoxide and magnesium vapor and sodium gas, substances that exist as solids or components of solids under normal conditions, but had been vaporized by the catastrophic heat of the impact. This atmosphere was dense and opaque, glowing with its own thermal radiation, pressing down on the magma ocean with a weight that would have crushed any structure humans have ever built. As the system radiated heat into space, the upper layers of the atmosphere began to cool. Cooling meant condensation. The vaporized rock reached a temperature at which it could no longer remain gaseous, and it began to precipitate out, falling back toward the surface in droplets and streams of liquid stone. This was the rain that was not rain, a downpour of molten silicates that splashed into the magma ocean below and mixed with the churning currents. The process was continuous and planet-wide, a global deluge that lasted for thousands of years, gradually transferring mass from the atmosphere back to the surface and allowing the atmosphere itself to thin and cool. The magma ocean did not solidify from the top down, as a frozen pond does. The physics of cooling rock under high pressure dictated a different pattern. As the temperature dropped, crystals began to form within the liquid magma, tiny seeds of solid matter that grew as more atoms attached themselves to the crystalline structure. The first crystals to form were olivine, a dense green mineral rich in magnesium and iron. Olivine crystals are heavier than the magma from which they precipitate, so they sank, drifting downward through the liquid rock like snowflakes falling through water, accumulating at the bottom of the magma ocean in a growing layer of crystalline mush. This process, repeated over millions of years, gradually solidified the Earth from the bottom up. The mantle formed first, built from the accumulated crystals that sank out of the magma ocean. The core had already differentiated during the collision itself, the dense iron from both Earth and Theia pooling at the center of the combined mass. What remained was the upper layer, the last portion of the magma ocean to solidify, and this would eventually become the crust. The crust formed not from sinking crystals but from floating ones, minerals that were less dense than the surrounding liquid and rose to the surface rather than falling to the bottom. On Earth, this process was complicated by the presence of water. Even in the Hadean, even in the immediate aftermath of the collision, Earth retained some water, locked in minerals and dissolved in magma and trapped in the thickening atmosphere. Water has a profound effect on the crystallization of silicate magmas. It lowers the melting point of rock, changes the sequence in which minerals crystallize, and prevents certain minerals from forming altogether. The plagioclase feldspar that might have floated to the surface of a dry magma ocean could not crystallize from a wet one. Earth's early crust formed through a different, more complex process involving volcanic activity and plate tectonics, processes that began remarkably early in planetary history. The Moon had no such complications. The Moon was dry. This is one of the most striking features revealed by the Apollo samples, and it remains one of the strongest pieces of evidence for the giant impact hypothesis. Lunar rocks are almost completely devoid of water and other volatile substances, elements and compounds that evaporate easily at high temperatures. The collision that formed the Moon generated such intense heat that these volatiles were driven off, boiled away into space, leaving behind only the most refractory materials, the substances with the highest melting points. The Moon was born dehydrated, and it has remained so ever since. Without water to interfere, the lunar magma ocean crystallized according to a straightforward sequence. First came olivine, sinking to form the deep mantle. Then came pyroxene, another dense mineral, adding to the growing cumulate pile at the bottom of the magma ocean. And then, after approximately 80% of the magma ocean had solidified, something different began to happen. The remaining liquid had become enriched in aluminum and calcium, elements that had been excluded from the earlier crystals. When this enriched liquid finally began to crystallize, it produced plagioclase feldspar, a mineral that is less dense than basaltic magma. The plagioclase crystals floated. They rose through the remaining liquid like bubbles through honey, drifting upward until they reached the surface, where they accumulated in a growing layer of solid rock. This rock was almost pure plagioclase, white and crystalline, reflecting sunlight with a brightness that would have been visible from Earth if anyone had been there to look. Scientists call this rock anorthosite, and it forms the bulk of the lunar highlands, the bright regions that cover most of the Moon's surface and stand in stark contrast to the dark maria that form the familiar face of the man in the Moon. The formation of the anorthosite crust was not instantaneous. Recent research suggests that the lunar magma ocean remained partially molten for far longer than early models predicted, perhaps 200 million years or more. The crystallization was not a simple freezing process, but a complex interplay between cooling, convection, and crystal settling. The magma ocean may have existed as a slurry for much of this time, a mixture of liquid and suspended crystals that was too thick to flow freely, but too fluid to support a solid crust. Scientists describe this state as slushy, borrowing another word from everyday experience and stretching it to cover conditions that everyday experience could never produce. Beneath the floating crust, the final dregs of the magma ocean were squeezed into a thin layer between the crystalline mantle below and the anorthosite above. This liquid was the last to solidify, and it contained everything that the earlier crystals had rejected: potassium, rare earth elements, phosphorus, uranium, thorium. Geochemists call this material KREEP, an acronym assembled from the chemical symbols and names of its dominant components. KREEP is radioactive, enriched in elements that decay over geological time and release heat as they do so. It would play a crucial role in the subsequent evolution of the Moon, providing a source of internal heat that drove volcanic activity for billions of years after the magma ocean solidified. The distribution of creep on the Moon is not uniform. It is concentrated almost entirely on the near side, the hemisphere that faces Earth, with very little present on the far side. This asymmetry is one of many differences between the Moon's two hemispheres, differences that would puzzle scientists for decades and that still are not fully explained. The creep concentration correlates with the distribution of the Maria, the dark basaltic plains that formed when volcanic eruptions flooded ancient impact basins with lava. It correlates with the thickness of the crust, which is thinner on the near side than the far side. It correlates with the thermal history of the Moon, which cooled unevenly because one hemisphere was always facing the hot young Earth, while the other faced the cold of deep space. The Earth and Moon were still close during this period of solidification. The tidal forces between them were immense, far stronger than anything we experience today. These forces did not merely raise bulges of rock on the surfaces of both bodies. They generated friction, heat, energy that was dissipated into the interiors of both worlds. On the Moon, tidal heating may have prolonged the lifetime of the magma ocean, keeping it molten for tens of millions of years longer than it would have lasted in isolation. On Earth, the tidal forces helped to drive convection in the mantle, stirring the interior and accelerating the differentiation of crust and core. The two bodies were also exchanging angular momentum, though neither possessed any awareness of this transaction. The Earth was rotating faster than the Moon orbited around it, and the tidal bulge raised on Earth by the Moon's gravity was carried slightly ahead of the Earth-Moon line by this rotation. The gravity of this offset bulge pulled forward on the Moon, accelerating it in its orbit. An accelerated orbit is a larger orbit. The Moon was spiraling outward, slowly, imperceptibly, climbing away from the Earth at a rate that would eventually slow to the 3.8 centimeters per year we measure today, but that was much faster in the early solar system when the two bodies were closer together. The Moon was also slowing down, not its orbital motion which was speeding up, but its rotation on its own axis. The tidal bulge raised on the Moon by Earth's gravity experienced friction as the Moon rotated, and this friction acted as a brake, gradually reducing the Moon's spin rate. The process continued until the Moon's rotation period matched its orbital period, until it took exactly as long for the Moon to turn once on its axis as it did for the Moon to complete one orbit around the Earth. At that point, the tidal bulge no longer moved relative to the Moon's surface. The friction ceased, and the system reached a stable configuration. The Moon became locked, one face always toward Earth, one face always away. This is why we see the same features on the Moon every night. This is why the man in the Moon never turns his head, why the Maria form the same pattern that our ancestors saw 100,000 years ago, why the lunar far side remained unknown until spacecraft flew around to photograph it. The Moon did not choose to show us one face. It was forced into this configuration by the same gravitational interaction that is still pushing it away from us today, the same interaction that is slowly lengthening our days and will eventually, billions of years from now, lock the Earth into the same synchronous rotation with the Moon. The magma oceans cooled. The crusts solidified. The rain of liquid rock gave way to the silence of solid stone. And for the first time since the collision, the Earth-Moon system achieved something resembling stability. It would not last. The young solar system was still full of debris, leftover planetesimals and asteroids and comets, objects that had not yet been swept up by the gravity of the major planets. This debris was about to announce its presence in the most violent way imaginable. The bombardment was coming. There is a question that children ask and adults forget to wonder about. Why does the Moon always show us the same face? We see the same craters every night, the same dark patches, the same pattern of light and shadow that humans have been interpreting as faces and rabbits and figures carrying bundles of sticks for as long as humans have looked upward. The moon rises and sets, it waxes and wanes, it travels across the sky from east to west, but it never turns. It never shows us its back. The far side remained a complete mystery until October of 1959, when the Soviet spacecraft Luna 3 swung around the moon and photographed what no human eye had ever seen. This is not a coincidence. The moon is locked. The term scientists use is tidal locking, or synchronous rotation, and it describes a state in which the rotation period of a body exactly matches its orbital period. The moon takes approximately 27 days to complete one orbit around the Earth. It also takes approximately 27 days to complete one rotation on its axis. These two periods are identical not by chance, but by physics, the inevitable result of gravitational forces acting over hundreds of millions of years. To understand how this happened, you must first understand what tides really are. We think of tides as the rise and fall of ocean water, the rhythm that governs the lives of fishermen and the schedules of coastal communities. This is true, but it is only part of the truth. Tides are not limited to water. They occur in any deformable body that experiences a non-uniform gravitational field. The Earth raises tides on the moon just as the moon raises tides on the Earth. These tides are not made of water because the moon has no water. They are made of rock. When the moon was young and still partially molten, the tidal bulge raised by Earth's gravity was substantial. The near side of the moon, facing Earth, was pulled outward by perhaps several kilometers. The far side bulged outward as well, though less dramatically because it was farther from Earth and experienced weaker gravitational pull. The moon became slightly elongated, stretched along the axis pointing toward Earth like an egg rather than a sphere. If the moon had not been rotating, this elongation would have been stable. The bulges would have remained fixed, always pointing toward and away from Earth, and no energy would have been dissipated, but the moon was rotating. In the aftermath of the giant impact, it was spinning rapidly, completing one rotation in just a few hours. This meant that the tidal bulge could not stay in one place. As the moon rotated, the bulge had to move, traveling across the lunar surface to keep pace with the changing direction of Earth's gravitational pull. Rock does not flow easily. Even molten rock has viscosity, resistance to deformation, and solid rock resists far more strongly. As the tidal bulge was dragged around the moon by its rotation, friction generated heat. This heat was dissipated into the lunar interior, radiated away into space, lost forever from the rotational energy of the moon. And energy lost from rotation means rotation slowed down. The process was gradual but relentless. Every rotation cost the moon a tiny fraction of its spin. Over thousands of years, the rotation period lengthened from hours to days. Over millions of years, it lengthened further. The tidal bulge moved more slowly as the rotation slowed, which reduced the friction, which slowed the rate of energy loss, which meant that the final approach to synchronization took far longer than the initial spin down. But the outcome was never in doubt. Given enough time, any moon close enough to its planet will eventually become tidally locked. The moon reached synchronous rotation early in its history, probably within the first 100 million years after its formation. Once locked, the tidal bulge became stationary. It no longer moved across the lunar surface, no longer generated friction, no longer dissipated energy. The system had reached equilibrium. The moon would show the same face to Earth forever, or at least until some external force disrupted the arrangement. The Earth has been undergoing a similar process, but in reverse. The moon raises tides on Earth, bulges of water and rock that are dragged around the planet by Earth's faster rotation. The Earth rotates once every 24 hours, but the Moon takes 27 days to orbit, so the tidal bulge on Earth is constantly being carried ahead of the Moon's position. This offset matters. The gravity of the bulge pulls on the Moon, and because the bulge is ahead of the Moon in its orbit, the pull is forward, accelerating the Moon in its orbital motion. An accelerated Moon moves to a higher orbit. This is counterintuitive, because we associate acceleration with increased speed, and the Moon in a higher orbit actually moves more slowly. But orbital mechanics follows its own logic. The Moon gains energy from the forward pull of Earth's tidal bulge, and that energy goes into climbing farther from Earth. The Moon is receding at a rate of 3.8 centimeters per year, a measurement made possible by the retroreflectors left on the lunar surface by Apollo astronauts. Scientists on Earth fire laser pulses at these reflectors and time how long the light takes to return. The precision is extraordinary, accurate to within a few millimeters, and it reveals that the Moon is measurably farther away this year than it was last year. The energy the Moon gains must come from somewhere. It comes from the Earth. Specifically, it comes from the rotational energy of the Earth, the spin that gives us day and night. As the tidal bulge transfers momentum to the Moon, the Earth slows down. The effect is small, approximately 2.3 milliseconds per century, but it accumulates. 400 million years ago, the day was only 22 hours long. 600 million years ago, it was 21 hours. In the distant past, when the Moon was young and close, the day may have been as short as 6 hours. We know this not from theoretical calculations alone, but from the fossil record. Corals grow in daily layers, thin bands of calcium carbonate deposited in rhythm with the cycle of light and dark. Ancient corals, preserved in rocks hundreds of millions of years old, show more of these daily bands per year than modern corals do. The years were the same length because Earth's orbit around the Sun has not changed significantly. But the days were shorter, which means there were more of them in each year. The fossils confirm what physics predicts. The system is still evolving. In the far future, billions of years from now, the Moon will have receded to a much greater distance, and the Earth's rotation will have slowed to match the Moon's orbital period. When that happens, the Earth and Moon will be mutually locked, each showing only one face to the other. A day on Earth will last approximately 47 of our current days. The Moon will hang motionless in the sky for observers on one hemisphere and will never be visible at all from the other hemisphere. Tides will cease because the tidal bulge will no longer move relative to the surface. This future will never arrive. Long before the Earth and Moon can reach mutual synchronization, the Sun will exhaust the hydrogen fuel in its core and expand into a red giant. The outer layers of the swollen Sun will extend past the current orbit of Venus, possibly past the orbit of Earth. Whether our planet will be consumed entirely or merely scorched into a cinder remains uncertain, but the Earth-Moon system as we know it will not survive. The dance that began with Theia's impact will end in fire, as all things in this universe eventually do. But that ending lies 5 billion years in the future. For now, the Moon continues its slow retreat, the Earth continues its slow deceleration, and every night the same face looks down on us that looked down on the dinosaurs, on the first mammals, on the first fish to crawl onto land, on the first cells to divide in the warm Archean oceans. The Moon has been watching for a very long time. It has seen everything that ever happened on the surface of this planet. It was watching before there was anything to see. The locking of the Moon was complete, its eternal gaze fixed upon the Earth. But the face it showed us was not yet the face we know. The craters had not formed. The Maria had not filled with lava. The Moon was still bright and uniform, a world of white anorthosite unmarked by the violence that was about to descend upon it. And then the sky began to fall. October 7th, 1959. A Soviet spacecraft called Luna 3 swung around the far side of the Moon, aimed its camera at a landscape no human had ever seen, and transmitted the first photographs back to Earth. The images were grainy, blurred, barely recognizable as pictures of a planetary surface. But they were enough to reveal something that no one had expected. The far side of the Moon looked nothing like the near side. This was not supposed to happen. The Moon was the Moon, a single body formed from a single event, rotating slowly in the void for 4.5 billion years. There was no obvious reason why one hemisphere should differ from the other. Yet the photographs from Luna 3 showed a surface dominated by craters, bright and densely packed, with almost none of the dark, smooth plains that give the near side its familiar appearance. The man in the Moon, it seemed, had no counterpart on the other side. The far side was all highlands, all mountains, all ancient battered crust. The dark maria were almost entirely absent. Scientists named this puzzle the Lunar Far Side Highlands Problem, a clinical term for what was really a profound mystery. The maria that cover 31% of the near side cover barely 1% of the far side. The crust on the far side is significantly thicker than the crust on the near side, in some places by tens of kilometers. The concentration of radioactive elements, the creep material left over from the crystallization of the magma ocean, is heavily skewed toward the near side. Everything about the Moon's two hemispheres suggests different histories, different thermal evolution, different exposure to the forces that shaped the early solar system. For decades, explanations remained elusive. Some researchers proposed that the asymmetry was primordial, built into the Moon from the moment of its formation by some quirk of the giant impact. Others suggested that the Moon had been struck by a large object early in its history, an impact that added extra crustal material to one hemisphere but not the other. Still others pointed to the influence of Earth, arguing that our planet's gravity or heat had somehow affected the near side differently than the far side. Each hypothesis had strengths and weaknesses, none fully explained all the observations. The most compelling explanation emerged only in the last decade, and it connects the asymmetry of the Moon's face to the same tidal forces that locked its rotation. When the Moon formed, it was close to the Earth, far closer than it is today, and the Earth was hot, still glowing with the residual heat of the giant impact, still molten in its outer layers, still radiating energy into space at a rate that would have been visible from neighboring planets. The Moon, tidally locked from early in its history, always presented the same face to this incandescent Earth. The near side was bathed in infrared radiation, heated from without as well as from within. The far side faced only the cold void of deep space, where the temperature is just a few degrees above absolute zero. This asymmetry in external heating had consequences for the way the magma ocean cooled and crystallized. Aluminum and calcium, the elements that combine with silicon and oxygen to form plagioclase feldspar, have relatively high vaporization temperatures. In the lunar magma ocean, these elements existed partly as vapor in the atmosphere that surrounded the molten Moon. On the hot near side, facing Earth, the temperatures remained high enough that aluminum and calcium stayed in the vapor phase longer. On the cold far side, they condensed earlier, snowing out of the atmosphere and accumulating in the solidifying crust. The far side crust grew thicker because it received more of these crust-forming elements. The near side crust remained thinner because the heat from Earth delayed the condensation process. A thicker crust is harder to penetrate. When the late heavy bombardment arrived, when asteroids hundreds of kilometers across slammed into the lunar surface, the consequences differed depending on where they struck. On the near side, with its thinner crust, the largest impacts punched through to the mantle below. Magma welled up through the fractured rock, flooding the impact basins with dark basaltic lava that solidified into the smooth plains we call maria. On the far side, the same size impacts could not breach the thicker crust. The basins formed. the rock shattered, but no magma reached the surface. The far side remained bright and cratered, a museum of ancient impacts unobscured by later volcanic flows. This explanation is elegant, but it may not be complete. Other factors likely contributed to the asymmetry. The concentration of creep on the near side meant that radioactive decay generated more heat in that hemisphere, keeping the interior warmer and more prone to volcanic eruptions. The pattern of convection in the lunar mantle, influenced by the tidal forces from Earth, may have preferentially transported heat toward the near side. Some researchers have even proposed that the Moon once had a companion, a smaller moonlet formed from the same debris disk, which eventually fell back and plastered itself onto the far side, adding extra crustal material in a slow-motion collision. The truth is probably a combination of many processes, a story more complex than any single mechanism can capture. The Moon's two faces are a palimpsest, a document written and overwritten by billions of years of geological history. Reading that document requires patience, multiple hypotheses, and a willingness to accept that some mysteries may never be fully resolved. What we can say with confidence is that the Maria formed from volcanic activity, and that this activity was concentrated on the near side. The largest Maria correspond to the largest impact basins, depressions carved by asteroids and comets during the first billion years of lunar history. Mare Imbrium, the great dark oval that forms the right eye of the man in the Moon, is roughly 1,100 kilometers across and was created by an impact approximately 3.9 billion years ago. Mare Serenitatis, Mare Tranquillitatis, Mare Crisium, each marks the grave of an ancient impactor, a wound subsequently healed by the dark blood of volcanic rock. The volcanism that created the Maria was not instantaneous. Radiometric dating of lunar basalts shows that the eruptions spanned more than 1 billion years, from about 4 billion years ago to less than 2 billion years ago. The youngest lava flows are found in Oceanus Procellarum, the largest of the Maria, which may have remained volcanically active until relatively recently in geological terms. The heat that drove these eruptions came from the radioactive decay of elements in the KREEP layer, a slow-burning furnace that kept the lunar interior warm long after the magma ocean had solidified. The far side, deprived of this volcanic resurfacing, preserves a much older landscape. The craters there have not been flooded or buried. They overlap and intersect, younger impacts cutting into older ones, creating a record of bombardment that stretches back to the earliest days of the solar system. The far side is a window into the past, a surface that has remained largely unchanged for 4 billion years, while the near side was repeatedly remade by volcanic floods. There is something poignant about this asymmetry. The face the Moon shows us is not its original face. It is a mask, a surface transformed by fire, smoothed by lava, marked by the dark stains of ancient eruptions. The true face of the Moon, the face it was born with, is the one it hides from us, the bright and battered far side that we could not see until we sent machines to look on our behalf. The Moon rotates once every 27 days, always keeping that same transformed face toward Earth. But it does not keep perfectly still. There are small wobbles, oscillations caused by the elliptical shape of the lunar orbit and the tilt of the Moon's axis. These wobbles, called librations, allow us to peek around the edges of the Moon over the course of a month, glimpsing an additional 9% of the surface that would otherwise remain hidden. Over time, we can see 59% of the Moon from Earth, though never more than half at any given moment. The remaining 41% stayed completely unknown until the space age. The differences between the two hemispheres are not limited to Maria and highlands. The far side has higher elevations on average, with mountains and crater rims that tower above the mean surface level. It contains the South Pole Aitken Basin, one of the largest and oldest impact structures in the solar system, a scar 2,500 kilometers across and more than 8 kilometers deep. This basin is so large that it excavated material from deep within the lunar crust, possibly even from the mantle, and yet it was never flooded with lava. The crust there, despite being thinner at the point of impact, was still apparently too thick for magma to break through in the volumes necessary to fill such an enormous depression. The South Pole Aitken Basin is a prime target for future exploration. Samples from its floor could reveal the composition of the deep lunar interior, material that has never been accessible before. They could provide new constraints on the age of the basin, which in turn would refine our understanding of the bombardment history of the inner solar system. They could contain clues about the formation of the moon itself, fragments of the original crust or mantle preserved beneath the debris of the impact. No human has ever visited the far side of the moon. No sample has ever been returned from that hidden hemisphere. The far side remains in many ways as mysterious as it was before Luna 3 sent back those grainy photographs more than 60 years ago. The moon wears two faces, one transformed by fire and one preserved in stone. It shows us only the transformed face, the dark-eyed countenance that has watched over humanity since before we were human. The original face, the bright and ancient face, remains turned away, gazing into the depths of space, waiting for the day when we finally walk across its mountains and stand in the shadow of its towering crater walls. That day may come within our lifetimes. Spacecraft are already returning to the moon, orbiters and landers and rovers, mechanical emissaries preparing the way for human footsteps. The far side will not remain hidden forever. But 4 billion years ago, neither side of the moon was safe. Neither side could hide from what was coming. The inner solar system had entered a period of chaos, and everything in it, Earth and Moon alike, was about to be subjected to a bombardment of staggering violence. For 500 million years, the inner solar system burned, not with the fire of stars, but with the fire of impact. Asteroids the size of mountains, comets trailing tails of vapor longer than the distance between Earth and Moon, planetesimals left over from the formation of the planets, objects that had been drifting in unstable orbits since the solar system was young, finally swept up by the gravity wells of the rocky worlds. They came by the thousands, by the tens of thousands, in a bombardment so intense that it reshaped every surface in the inner solar system. Scientists call this period the Late Heavy Bombardment, though the name is somewhat misleading. It was not a single event, but an epoch stretching from approximately 4 billion years ago to perhaps 3.5 billion years ago. And it was not uniformly heavy throughout. The bombardment rate fluctuated, spiking at certain times when gravitational perturbations sent fresh waves of debris cascading inward from the outer solar system. The peak of the bombardment, the period of most intense cratering, occurred around 3.9 billion years ago. This is the age recorded in the oldest impact melt rocks brought back by the Apollo astronauts, samples that crystallized from pools of molten stone generated by the heat of collision. The cause of the late heavy bombardment remained mysterious for decades. The planets had formed 4.5 billion years ago. By 4 billion years ago, most of the original debris should have been cleared from the inner solar system, swept up by planetary gravity or ejected into interstellar space. Where did this late surge of impactors come from? Why did the bombardment intensify hundreds of millions of years after the planets had finished forming? The answer, according to the most widely accepted model, lies in the outer solar system, in the gravitational dance of the giant planets. Jupiter, Saturn, Uranus, and Neptune did not form in their current orbits. They migrated, shifting their positions over hundreds of millions of years as they exchanged angular momentum with the disk of debris that surrounded the young Sun. At some point, Approximately 4 billion years ago, this migration triggered a catastrophic rearrangement. Jupiter and Saturn crossed a critical orbital resonance, a configuration in which Saturn completed exactly 2 orbits for every 1 orbit of Jupiter. This resonance destabilized the entire outer solar system. Uranus and Neptune were flung outward into regions they had never occupied before, ploughing through a vast disk of icy bodies that had been peacefully orbiting beyond the original positions of the giant planets. This disk, the primordial ancestor of today's Kuiper Belt, contained billions of comets and icy asteroids. The passage of Uranus and Neptune scattered these objects in all directions, sending many of them spiraling inward toward the Sun. The inner solar system, which had been relatively quiet for hundreds of millions of years, was suddenly flooded with impactors. The Moon recorded this bombardment with perfect fidelity. Without an atmosphere to burn up incoming objects, without water to erode the craters they left behind, without plate tectonics to recycle the crust and erase ancient features, the lunar surface preserved every impact like a diary written in stone. The great basins that would later fill with lava to become the Maria were carved during this period. Mare Imbrium, Mare Serenitatis, Mare Nectaris, Mare Crisium. Each dark plane visible on the face of the Moon marks a wound inflicted during the late heavy bombardment. A scar from an impactor tens or hundreds of kilometers across, striking at velocities of 20 kilometers per second or more. The impact that created Mare Imbrium was one of the largest. The asteroid that struck was perhaps 250 kilometers in diameter, a worldlet in its own right, carrying enough kinetic energy to excavate a basin more than 1,000 kilometers across. The shock wave from the impact propagated through the lunar crust, fracturing rock to depths of tens of kilometers, creating a pattern of radial and concentric faults that geologists can still trace today. The material ejected from the basin was flung across the entire lunar surface, depositing a layer of debris that serves as a stratigraphic marker, a boundary between before and after. Earth suffered equally, perhaps more so. Our planet is larger than the Moon, which means its gravitational cross-section is larger, which means it intercepted more impactors. Computer models suggest that Earth was struck by objects large enough to vaporize the oceans multiple times during the late heavy bombardment. Each such impact would have sterilized the surface, raising global temperatures to hundreds of degrees Celsius, boiling away any liquid water, killing any life that might have begun to emerge. The early Earth was not a cradle for life. It was a furnace, repeatedly sterilized, repeatedly reset to sterile conditions, and yet life appeared. The oldest convincing evidence for life on Earth dates to approximately 3.5 billion years ago, just as the late heavy bombardment was winding down. Some researchers argue for even earlier origins, pointing to chemical signatures in rocks 3.8 or even 4.1 billion years old that might indicate biological activity. If these interpretations are correct, then life emerged during the bombardment itself, somehow surviving the repeated catastrophes, perhaps finding refuge in the deep ocean or in underground rock formations where the heat of impact could not reach. The Moon offers no such evidence. The lunar surface was sterilized as thoroughly as Earth's, but there were no oceans to provide sanctuary, no deep crust to shelter microorganisms. If life ever existed on the Moon, which is unlikely given the absence of water and atmosphere, it left no trace. What the Moon offers instead is a record, a chronicle of the bombardment that Earth could not preserve. By studying the lunar craters, by dating the impact melt rocks returned by Apollo, scientists can reconstruct the history of violence that both worlds endured. This history is more complex than early models suggested. Recent research has challenged the idea of a sharp spike in bombardment at 3.9 billion years ago. Analysis of lunar samples using new isotopic techniques indicates that large impacts occurred earlier than previously thought, perhaps as early as 4.3 billion years ago. The clustering of ages around 3.9 billion years, which seemed so striking in the original Apollo data, may be an artifact of sampling bias. Most of the Apollo landing sites were located near Mare Imbrium, and most of the impact melt rocks collected may have been produced by that single enormous impact, rather than by multiple independent events. The picture emerging from current research is one of extended bombardment rather than sudden cataclysm. The rate of impacts declined steadily from the formation of the planets, punctuated by occasional spikes when gravitational perturbations sent fresh debris cascading inward. The late heavy bombardment was not a single event, but the tail end of a process that began with planetary formation itself, a long and violent cleanup of the debris left over from the birth of the solar system. By 3.5 billion years ago, the cleanup was largely complete. The inner solar system had been swept clear of most large debris. Impacts still occurred and still occur today, but at rates so low that a given location on a planetary surface might wait hundreds of millions of years between significant strikes. The Moon's surface, so thoroughly cratered during the bombardment, has changed little in the 3.5 billion years since. The Maria flooded with lava, smoothing some regions and covering others, but the highland crust remains essentially as it was when the bombardment ended. The craters we see today are the same craters that would have been visible to any observer 3 billion years ago. Earth, by contrast, has erased almost all evidence of its bombardment history. The oldest rocks on our planet date to about 4 billion years ago, and they are rare, preserved only in a few isolated locations where geological processes have not recycled them. The oldest intact crust is younger still. Plate tectonics, the constant creation and destruction of crustal material at mid-ocean ridges and subduction zones, has processed the surface of the Earth multiple times since the bombardment ended. We know Earth was struck because we can see the scars on the Moon and infer that our planet could not have escaped. But the direct evidence, the craters and the impact melt rocks, has been swallowed by the planet's own geological activity. This is why the Moon matters. Not because it is beautiful, though it is. Not because it has inspired poetry and mythology and the dreams of explorers, though it has done all these things. The Moon matters because it remembers what Earth has forgotten. It carries a record of the early solar system that no other body can provide, a history written in craters and preserved in stone. When we study the Moon, we are not studying a dead world. We are reading a diary of our own past, a chronicle of violence that made us what we are. The bombardment ended. The rain of stone from the sky slowed to a trickle and then to almost nothing. The inner solar system entered a new era, one of relative peace, one in which the dominant processes were no longer impacts and collisions but slower transformations. Volcanic eruptions, tectonic movements, the gradual evolution of atmospheres and oceans. On Earth, this peace allowed life to gain a foothold, to spread, to diversify, to eventually produce organisms capable of looking up at the Moon and wondering how it came to be. The Moon had witnessed all of this. It had been watching since the beginning, since the day it was born from fire and chaos, since before there was anything on Earth worth watching. And it would continue to watch, silent and patient as life transformed the planet below. The scars of bombardment faded into the background. The craters became familiar features rather than fresh wounds, and the Moon settled into its role as Earth's companion, a role it would play for billions of years to come. A role that, scientists would eventually discover, may have been essential to making Earth a world where life could thrive. Tilt the Earth 5 degrees and the climate shifts. Tilt it 10 degrees and the seasons become extreme. summers scorching and winters brutal across latitudes that currently enjoy temperate weather. Tilt it 20 degrees more, and the planet becomes almost unrecognizable. A world where the poles sometimes point nearly toward the sun, where ice ages and heat waves alternate in patterns that would make agriculture impossible, where the slow evolution of complex life might never have occurred. The Earth is tilted at 23.5 degrees. This number is not random. It is not an accident of formation, not a frozen relic of some primordial spin. It is a negotiated value, a compromise between the forces that would push the Earth's axis in one direction and the forces that would pull it in another. And the primary negotiator, the gravitational anchor that keeps this compromise stable, is the Moon. In 1993, French astronomer Jacques Lascar published a paper that changed how scientists thought about planetary habitability. Using computer simulations that tracked the gravitational interactions between the planets over millions of years, Lascar demonstrated that the Earth's axial tilt is inherently unstable. Without some stabilizing influence, the tilt would wander chaotically, swinging from nearly 0 degrees to as much as 85 degrees over timescales of tens of millions of years. The culprits are Jupiter and Venus, whose gravitational tugs create subtle perturbations in Earth's orbit that accumulate over time, pushing and pulling at the orientation of our planet's spin axis. Mars provides a cautionary example. The red planet has no large moon, only 2 tiny captured asteroids that exert negligible gravitational influence. Without a stabilizing companion, the Martian axial tilt has varied dramatically over its history, ranging from about 10 degrees to more than 60 degrees. These variations happen on timescales of millions of years, slow by human standards, but fast by geological ones. The consequences for climate are severe. When Mars is tilted at a high angle, its poles receive intense sunlight during summer, causing frozen carbon dioxide and water ice to sublimate into the atmosphere. When the tilt is low, the poles remain in permanent shadow, trapping volatiles in frozen reservoirs. This climatic instability may be one reason why Mars lost most of its atmosphere and surface water, transforming from a potentially habitable world into the cold desert we see today. Earth avoided this fate because of the Moon. The lunar gravitational influence adds a large, steady component to the torque on Earth's spin axis, overwhelming the smaller perturbations from other planets. The Moon does not eliminate axial variation entirely. Earth's tilt oscillates between about 22.1 degrees and 24.5 degrees over a cycle of roughly 41,000 years, a pattern known as obliquity variation. But this is a gentle oscillation, a slow breath compared to the violent swings that would occur without lunar stabilization. The difference between 22 and 24 degrees is the difference between slightly milder and slightly more extreme seasons. The difference between 23 and 85 degrees would be the difference between a habitable world and an uninhabitable one. Recent research has complicated this picture somewhat. Computer simulations published in 2011 by Jack Lissower and his colleagues at NASA suggested that a moonless Earth might not be as unstable as Lascar's earlier work implied. Using more powerful computers and longer simulation times, they found that Earth's tilt would vary more without the Moon, but the most extreme excursions would occur only on timescales of billions of years, not millions. The climate would be less stable, but perhaps not catastrophically so. Life, given enough time, might adapt. This debate remains unresolved. The answer depends on initial conditions, on the precise configuration of the solar system, on factors that are difficult to constrain with certainty. What seems clear is that the Moon provides at least some stabilizing influence, even if the magnitude of that influence is still being quantified. A moonless Earth would be a different world, perhaps not lifeless, but certainly less predictable, subject to climatic variations that would challenge any biosphere. The Moon's influence extends beyond axial stability. There are the tides, of course, those twice-daily risings and fallings of the ocean that have marked time for as long as there have been shores to wash against. The tides are not merely a curiosity, not merely a force to be reckoned with by sailors and coastal engineers. They may have played a role in the origin of life itself. The boundary between land and sea is a chemically dynamic environment. Tidal pools fill and drain, concentrating dissolved substances as water evaporates, then diluting them again as the tide returns. This cycle of wetting and drying, repeated twice daily for billions of years, creates conditions that are difficult to replicate elsewhere. Organic molecules are concentrated, brought into contact with mineral surfaces that can catalyze reactions, exposed to ultraviolet radiation that can drive chemical transformations. Some origin of life researchers believe that this tidal zone, this ever-changing boundary between wet and dry, may have been the crucible in which the first self-replicating molecules emerged. Without the moon, Earth would still have tides. The sun also exerts a tidal force on our planet, though it is less than half as strong as the lunar tide. A moonless Earth would experience smaller tides, less extreme variations between high and low water, a gentler rhythm of wetting and drying. Whether this would have prevented the origin of life, delayed it, or merely changed its character is impossible to know. The question touches on one of the deepest mysteries in science, the transition from chemistry to biology, and any answer must be speculative. What is not speculative is the role the moon has played in shaping Earth's rotation. 4 billion years ago, the day was perhaps 6 hours long. The Earth spun so fast that the Coriolis effect, the apparent deflection of moving objects caused by rotation, would have been far stronger than it is today. Winds would have been more intense, weather patterns more chaotic, the circulation of the oceans more vigorous. Some researchers have suggested that this rapid rotation would have made the early Earth more hostile to life, though others argue that the thicker atmosphere of the time would have moderated the effects. The moon slowed us down. Tidal friction, the same process that is still lengthening our days by milliseconds per century, has been operating since the moon formed. The energy extracted from Earth's rotation has been transferred to the moon's orbit, pushing our companion outward while bleeding away the spin that once made our planet whirl like a top. The slowing has been gradual, imperceptible on human timescales, but transformative over geological time. The 24-hour day we take for granted is a gift from the moon, a rhythm imposed by gravity, a tempo set by the tidal dance between two worlds. There is another gift, one that will not last forever, the total solar eclipse. The sun is 400 times larger than the moon. It is also, by a coincidence that borders on the miraculous, almost exactly 400 times farther away. This means that the sun and moon appear almost exactly the same size in Earth's sky, each covering about half a degree of arc, each fitting precisely over the other when their orbits align. During a total solar eclipse, the moon blocks the brilliant disk of the sun so perfectly that the solar corona becomes visible, a halo of pearly white light that is normally lost in the sun's glare. The corona is the sun's outer atmosphere, a region of million-degree plasma that extends far into space, and it can only be studied from Earth during the few minutes of totality that a solar eclipse provides. This alignment is temporary. The moon is receding, as we have seen, at 3.8 centimeters per year. In the distant past, when the moon was closer, it would have appeared larger than the sun, completely blocking the disk and some of the corona as well. In the distant future, when the moon has receded far enough, it will appear smaller than the sun, and total eclipses will no longer occur. Only annular eclipses will remain, events in which a ring of the sun's brilliant surface remains visible around the dark lunar disk. We live in a window of time, perhaps a few 100 million years wide, during which the moon and sun appear so nearly matched that total eclipses are possible. There is no physical law that requires this. No principle of planetary formation dictates that a moon should appear the same size as its star from the surface of its planet. In all the solar system, Earth is the only world where this coincidence occurs. It is a gift, an accident, a cosmic alignment that allows us to see something we would otherwise never see. Whether this alignment has any significance beyond the aesthetic is unclear. Total eclipses have certainly influenced human history, inspiring awe and terror in ancient peoples, driving the development of astronomy as early observers tried to predict when the sun would disappear from the sky. But the eclipses themselves are not necessary for life. They are a bonus, a spectacular flourish added to a relationship that would be meaningful even without them. The moon has given us stable seasons, gentle tides, long days, and perfect eclipses. It has watched over the Earth since before there was anything to watch, since the first oceans condensed from the steam of the cooling crust, since the first microbes divided in the warm primordial waters, since the first fish crawled onto land and the first mammals scurried beneath the feet of dinosaurs. It will continue watching for billions of years more, until the sun swells and consumes us both, until the dance that began with Theia's impact finally ends in the fire of a dying star. And there is one more secret the moon has kept, one that scientists discovered only recently, one that connects the collision that created the moon to the very ground beneath your feet. Theia did not vanish entirely. Part of her is still here. In the 1980s, something strange appeared in the data. Seismologists had been mapping the interior of the Earth for decades, using earthquakes as natural probes. When a large earthquake occurs, it sends waves rippling through the planet, waves that travel at different speeds depending on the density and composition of the material they pass through. By recording these waves at stations around the world, scientists can construct images of Earth's interior, much as a medical ultrasound constructs images of a fetus from reflected sound. The images revealed a planet of concentric layers, a solid inner core of iron and nickel, unimaginably hot but squeezed solid by the pressure of everything above it. A liquid outer core, also iron, churning with convection currents that generate Earth's magnetic field. A thick mantle of silicate rock, solid but plastic, flowing over geological timescales like honey flows over human ones. And a thin crust, the skin of the planet, the only part we ever see or touch. But within the mantle, at the very bottom where rock meets the molten iron of the outer core, the seismic waves behaved strangely. In two regions, one beneath Africa and one beneath the Pacific Ocean, the waves slowed down. They lost velocity as they passed through these zones, as if the rock there were different somehow, denser or hotter or compositionally distinct from the surrounding mantle. The anomalies were enormous, each one roughly the size of a continent, each one extending upward from the core mantle boundary for hundreds of kilometers. Scientists named these structures large low-velocity provinces, a technical term that conveyed nothing of their mystery. LLVPs, as they came to be abbreviated, were unlike anything else in the Earth's interior. They were too large to be random variations in temperature. They were too stable to be transient features of mantle convection. They appeared to be permanent fixtures of the deep Earth, structures that had existed for a very long time, perhaps for most of planetary history. For decades, the origin of the LLVPs remained unexplained. Some researchers proposed that they were accumulations of subducted oceanic crust, slabs of rock that had been carried down into the mantle by plate tectonics and had piled up at the bottom like sediment on an ocean floor. Others suggested they were primordial features, remnants of the original differentiation of the Earth that had somehow survived 4.5 billion years of convective stirring. Still others argued that they were thermochemical piles, regions where heat and exotic chemistry combine to create rock with unusual properties. Then, in 2023, a team of researchers led by Chen Yuan of the California Institute of Technology and Arizona State University proposed a radical new explanation. The LLVPs, they argued, are not native to the Earth at all. They are pieces of Theia. The hypothesis emerged from a synthesis of geophysics and planetary science. Yuan and his colleagues had been studying the giant impact, running computer simulations of the collision that created the Moon, when they noticed something unexpected. In their models, the impact did not completely homogenize the two colliding bodies. Much of Theia was vaporized or ejected into orbit, eventually coalescing into the Moon. But some of Theia's mantle, the iron-rich silicate rock that surrounded her core, was delivered directly into Earth's lower mantle. And because this material was denser than the surrounding terrestrial rock, it sank. It drifted downward through the magma ocean, through the solidifying mantle, until it reached the bottom, the core mantle boundary, where it accumulated in great piles that could not sink any further. The simulations showed that this Theian material would not mix with the rest of the mantle. The lower mantle remained cooler than earlier models had assumed, too viscous to thoroughly blend the alien rock with native terrestrial material. The dense blobs of Theia's mantle would have descended as coherent masses, like drops of oil sinking through water, maintaining their compositional distinctiveness even as they settled into their final resting places. 4.5 billion years later, those blobs are still there. They have survived the entire history of the Earth, the formation of the crust, the onset of plate tectonics, the evolution and extinction of countless species, the rise of intelligence, the development of seismology. They are sitting beneath Africa and the Pacific Ocean right now, continent-sized remnants of a world that died before the Earth truly began. The evidence supporting this hypothesis is circumstantial but compelling. The LLVPs are enriched in iron oxide relative to the surrounding mantle, which is consistent with Theia having formed farther from the Sun where iron-rich materials were more abundant. The density contrast between the LLVPs and the ambient mantle matches what simulations predict for Theian material. The locations of the LLVPs, roughly antipodal to each other, are consistent with the geometry of the giant impact and the subsequent settling of dense debris. And the sheer longevity of the structures, their persistence through billions of years of mantle convection, suggests that they are anchored by compositional density rather than thermal buoyancy. If the hypothesis is correct, the implications are profound. The Moon is not the only remnant of Theia. The Moon is what escaped, what was flung into orbit by the violence of the collision. The LLVPs are what remained behind, what was swallowed by the Earth and buried at the bottom of the mantle. The Moon and the LLVPs are siblings, children of the same destroyed world, separated at birth and reunited only in the theories of 21st century science. The LLVPs may have influenced the evolution of the Earth in ways we are only beginning to understand. They are associated with deep mantle plumes, columns of hot rock that rise from the core mantle boundary and punch through the overlying mantle to create volcanic hotspots at the surface. Hawaii and Iceland, two of the most volcanically active regions on Earth, sit above plumes that originate near the edges of the LLVPs. The chemical signature of lavas from these hotspots is subtly different from the signature of mid-ocean ridge basalts, suggesting that the plumes tap a deep reservoir of compositionally distinct material. That reservoir may be Theia. There is something almost mythological about this discovery. In Greek legend, Theia was a titan, one of the elder gods who ruled before the Olympians. She was the mother of Helios the sun, Selene the moon, and Eos the dawn. When scientists named the Mars-sized impactor after her, they did not know how apt the name would prove to be. Theia gave birth to the Moon, literally, her body torn apart to provide the raw material from which our satellite formed. But she also gave birth to something else, Or rather, she donated her heart to the Earth, her iron-rich core merging with our planet's core, her mantle sinking to rest at the boundary between core and mantle. Theia is not gone. She is here. She is above us in the grey regolith of the lunar highlands and the dark basalt of the Maria. She is below us in the continent-sized anomalies that seismic waves reveal at the bottom of the mantle. She is, in a very real sense, the foundation on which we stand. The collision that created the moon was not simply destruction, it was transformation. Two worlds became one, their materials mixing and separating and settling into new configurations. The Earth we know, the Earth with its large iron core and its thin silicate crust and its anomalous LLVPs, is not the planet that existed before Theia arrived. It is a hybrid, a merger, a world assembled from the wreckage of a cosmic catastrophe. We are living on that wreckage. Every time we walk on solid ground, we walk on rock that was shaped by the giant impact. Every time we look up at the moon, we see the part of Theia that escaped. Every time seismologists map the deep Earth, they trace the outline of Theia's remains. The story of the moon is also the story of the Earth. They cannot be separated. They were born together, forged in the same fire, and they have been dancing together ever since. The moon pulling at the tides and stabilizing the axis and slowly receding, the Earth slowing its rotation and watching its companion drift away. They are partners in a waltz that began 4.5 billion years ago and will continue until the sun puts an end to both of them. Theia was the uninvited guest whose arrival transformed the party. She came from the Lagrange point where she had been hiding. She collided with the proto-Earth in a cataclysm of unimaginable violence, and she left behind two gifts, a moon in the sky and a heart in the ground. We are still learning to appreciate those gifts. We are still tracing their consequences, still mapping the structures they created, still reconstructing the event that made us possible. The scientists who first returned samples from the moon did not know they were collecting pieces of Theia. The seismologists who first detected the LLVPs did not know they were mapping her grave. But now we know, and that knowledge changes how we see ourselves. We are not simply residents of Earth looking up at a separate body called the moon. We are children of a collision, inheritors of a catastrophe, built from the merged remains of two worlds that died so that we could live. 21.8 kilograms. That is the weight of the first moon rocks ever held by human hands on Earth. Not much, really. The weight of a medium-sized dog or a toddler, or a suitcase packed for a short trip. Neil Armstrong and Buzz Aldrin had 2 hours and 31 minutes on the lunar surface. 2 hours and 31 minutes to make history, to plant a flag, to set up experiments, to collect samples of rock and soil that had been lying untouched for billions of years. They worked quickly, scooping regolith into bags, picking up rocks that caught their eye, photographing everything so that scientists back home would know exactly where each sample came from. When they returned to Earth on July 24, 1969, those 21.8 kilograms of lunar material entered a specially designed facility in Houston called the Lunar Receiving Laboratory. Scientists had prepared for this moment for years, building glove boxes and vacuum chambers and sterilization equipment, designing protocols to prevent contamination in either direction. The moon rocks might carry unknown pathogens that could devastate life on Earth, or terrestrial microbes might contaminate the samples, obscuring whatever biological or chemical signatures they contained. Nobody knew what to expect. Nobody had ever held a piece of another world before. The first thing the scientists noticed was the smell. When the astronauts opened their helmets back in the lunar module after their moonwalk was complete, they detected an odor in the cabin, a sharp, acrid scent that reminded some of them of gunpowder. This was the smell of the moon, or rather, the smell of lunar dust reacting with the oxygen and moisture of the cabin atmosphere. The dust had been chemically inert for billions of years, exposed only to the vacuum of space and the harsh radiation of the sun. Contact with air triggered reactions that released volatile compounds, a sensory glimpse of the alien chemistry waiting to be discovered. The samples themselves were unlike any rocks found on Earth. Some were basalts, dark and fine-grained, similar in some ways to the volcanic rocks of Hawaii or Iceland. But these basalts were old, staggeringly old, 3.6 to 3.9 billion years by radiometric dating. They had crystallized from lava when life on Earth was still limited to single cells, when the oceans were young and the continents had barely begun to form. And they contained minerals that told stories of conditions no terrestrial rock could record. One mineral found in the Apollo 11 samples was entirely new to science. It was a titanium-rich oxide that had never been observed on Earth, and the scientists who discovered it named it armalcolite, an amalgam of the first syllables of Armstrong, Aldrin, and Collins, the 3 astronauts of the Apollo 11 mission. Armalcolite was later found in a few rare terrestrial locations, but its discovery on the Moon came first. The Moon had given humanity a new mineral, a new entry in the catalogue of substances that exist in the universe. More significant than any single mineral was what the samples revealed about the Moon's history. Before Apollo, scientists debated whether the Moon had ever been geologically active. Some argued that the lunar surface was primordial, unchanged since the Moon accreted from the solar nebula alongside the Earth. Others proposed that the Moon had formed hot, that it had differentiated into layers, that volcanism had reshaped its surface over billions of years. The samples settled the debate. The basalts were volcanic, unmistakably so. They had crystallized from molten lava. The Moon had been alive once, geologically speaking. It had a history. The samples also contained fragments of a rock type that would prove crucial to understanding lunar origins. Mixed into the regolith, broken and scattered by billions of years of impacts, were small pieces of anorthosite, a rock composed almost entirely of plagioclase feldspar. Anorthosite is rare on Earth, found in only a few locations where unusual geological processes concentrated this single mineral into nearly pure masses. On the Moon, anorthosite was everywhere, at least in the highlands. The bright regions visible from Earth, the regions between the dark Maria, were made of this pale, ancient rock. The existence of anorthosite on such a scale demanded explanation. Plagioclase feldspar is less dense than basaltic magma, which means it floats. If the outer layers of the Moon had once been molten, if there had been a global magma ocean covering the lunar surface, then plagioclase crystals forming in that ocean would have risen to the top, accumulating in a floating crust of anorthosite. This was the magma ocean hypothesis, and the Apollo samples provided its strongest support. The Moon had been born molten, wrapped in an ocean of liquid rock hundreds of kilometers deep, and the anorthosite highlands were the frozen froth of that primordial sea. Each subsequent Apollo mission brought back more samples and deeper understanding. Apollo 12 landed in Oceanus Procellarum and returned basalts younger than those from Apollo 11, demonstrating that lunar volcanism had continued for hundreds of millions of years. Apollo 14 collected samples from the Fra Mauro Formation, debris from the impact that created Mare Imbrium, allowing scientists to date that cataclysmic event to approximately 3.9 billion years ago. Apollo 15 explored the Hadley Riley and the Apennine Mountains, returning the Genesis rock, a sample of ancient anorthosite that crystallized 4.1 billion years ago in the primordial magma ocean. Apollo 16 ventured into the lunar highlands proper, the bright terrain that covers most of the far side and much of the near side outside the Maria. The samples confirmed that the highlands are indeed ancient, the oldest surviving crust on the Moon, battered by billions of years of impacts, but never resurfaced by volcanic flows. And Apollo 17, the final crewed mission to the Moon, landed in the Taurus-Littrow Valley, where astronaut Harrison Schmitt, the only professional geologist to walk on the lunar surface, discovered orange soil, tiny beads of volcanic glass that had erupted from the lunar interior 3.7 billion years ago. In total, the 6 Apollo missions that landed on the Moon returned 382 kilograms of samples, more than 2,000 individual rocks, drill cores that penetrated meters below the surface, regolith scooped from craters and plains and mountain slopes. These samples have been studied continuously for more than 50 years, and they are still yielding new discoveries. Techniques that did not exist in 1969, instruments that had not been invented, questions that had not been asked, all of these have been brought to bear on the Apollo collection, extracting information that the original scientists could never have imagined. The isotopic composition of lunar oxygen matches terrestrial oxygen almost exactly. This was a puzzle when first discovered, because the giant impact hypothesis predicts that the Moon should be made mostly of Theia, and Theia, having formed in a different part of the solar system, should have had a different oxygen signature. The close match suggested either that Theia and the proto-Earth formed from the same reservoir of material, or that the impact was so violent that it thoroughly mixed the two bodies before the Moon coalesced. Recent high-precision measurements have detected subtle differences between lunar and terrestrial oxygen, differences that may finally be revealing Theia's distinct contribution. The samples also revealed what the Moon lacks. Water is almost entirely absent from lunar rocks, as are other volatile substances that evaporate easily at high temperatures. This depletion is consistent with the giant impact, which would have generated enough heat to drive off any volatiles present in the original material. The Moon was born dry and has remained dry ever since, at least in its rocks. Ice may exist in permanently shadowed craters near the poles, deposited by comets over billions of years, but this is a later addition, not a primordial feature. There is no evidence of life in the lunar samples, nor any indication that life ever existed on the Moon. This was expected, but still confirmed by exhaustive testing. The Moon has no atmosphere to speak of, no liquid water, no protection from solar radiation, no source of energy that biological processes could exploit. It is sterile and has always been sterile, a world where chemistry never made the leap to biology. What the Moon offers instead is memory. The lunar surface is a museum of the early solar system, a record of events that Earth has long since erased. The impact history, the volcanic history, the gradual accumulation of the regolith, the implantation of solar wind particles in the topmost layers of soil, all of these are preserved on the Moon with a fidelity that no other body can match. When scientists study lunar samples, they are not just studying the Moon. They are studying the conditions that prevailed when life was emerging on Earth, the flux of impactors that threatened early organisms, the intensity of solar radiation before the ozone layer formed, the chemical environment of the inner solar system during its first billion years. The Apollo samples changed everything. Before 1969, the Moon was a mystery. Its origin debated, its composition unknown, its history a matter of speculation. After Apollo, the Moon became a known world, a world with a story that scientists could read in the chemistry of its rocks. The giant impact hypothesis, the magma ocean, the late heavy bombardment, the formation of the Maria, all of these ideas either emerged from or were confirmed by the study of lunar samples. The rocks that Armstrong and Aldrin collected in 2.5 hours of frantic work have been teaching us about our origins for more than half a century. Some of those rocks have never been opened. NASA anticipating that future technology would allow more sophisticated analysis than 1969 instruments could provide, sealed a portion of the Apollo samples in special containers and stored them for later study. In 2019, 50 years after the first landing, some of these pristine samples were finally opened. Scientists applied techniques that did not exist in the Apollo era. Mass spectrometry methods capable of detecting atoms in parts per trillion, imaging technologies that could resolve features smaller than a wavelength of light. The samples are still speaking, still yielding secrets, still teaching us about the world that died to give us our moon. And they will continue to speak. The Apollo collection is not exhausted. New questions arise as science advances. Questions that require new measurements, new analyses, new ways of interrogating the ancient stones. Each generation of scientists brings fresh perspectives, fresh tools, fresh curiosity. The rocks that crossed the void between worlds more than 50 years ago remain as scientifically valuable as ever, perhaps more so because we now know how much they have to tell us. 21.8 kilograms from Apollo 11, 34.3 from Apollo 12, 42.3 from Apollo 14, 77 from Apollo 15, 95.71 from Apollo 16, 110.52 from Apollo 17. 382 kilograms in total, the weight of a small motorcycle, the weight of 4 or 5 human beings, the weight of answers to questions that humanity had been asking since the first ancestor looked up at the night sky and wondered what that pale light might be. The moon is no longer a mystery. It is a history written in stone, waiting to be read. The moon is out there tonight. It may be rising over your city as you listen to these words, climbing above the rooftops and the trees, casting shadows that stretch and shorten as it arcs across the sky. Or it may be setting, sinking toward the horizon, its light fading as the glow of dawn approaches. Perhaps it is hidden by clouds, or perhaps it has not yet risen where you are, still waiting below the curve of the earth for its turn to appear. But it is there. It is always there. It has been there every night of your life, every night of your parents' lives, every night since the first human looked up and noticed that pale glow moving among the stars. 4.5 billion years, that is how long the moon has been watching. It watched when the earth was young, when the surface was molten rock and the sky was thick with vaporized stone. It watched when the first oceans formed, condensing from the steam of a cooling world, filling basins that would one day become the Atlantic and the Pacific. It watched when the first life emerged, whatever form that life took, in whatever warm pool or deep-sea vent or tidal flat it first assembled itself from chemistry into biology. The moon was there. The moon saw. It watched when the first fish crawled onto land, dragging itself through the mud on stubby fins that would eventually become legs. It watched when the dinosaurs ruled, when great reptiles shook the ground with their footsteps and pterosaurs filled the sky with leathery wings. It watched when the asteroid came 66 million years ago and ended that reign in fire and darkness. It watched when the mammals emerged from their burrows and began the long climb toward intelligence. It watched when the first hominids stood upright on the African savanna, when they learned to make tools, when they discovered fire, when they painted images on cave walls and buried their dead with flowers. The moon watched all of this. It did not judge. It did not intervene. It simply watched as it watches now, as it will continue to watch for billions of years to come. And through all that watching, it has been drifting away. Slowly, imperceptibly, centimeter by centimeter, the moon has been climbing to a higher orbit. The tides that its gravity raises on Earth, the same tides that may have cradled the first life in their rhythm of wetting and drying, are pushing it outward. The moon that hung huge and red in the sky of the young Earth, close enough to raise 1,000-foot tides in the magma ocean, is now 250,000 miles away. It looks small from here, small enough to cover with your thumb held at arm's length. But it is the same moon. It has simply been walking backward, step by tiny step, for 4.5 billion years. In another 600 million years, give or take, the moon will be too far away to completely cover the sun. The total solar eclipses that have awed and terrified humanity since before history began will cease. There will still be eclipses, but the moon will appear too small to block the entire solar disk, and a ring of brilliant sunlight will always remain visible around the dark lunar silhouette. Future beings, if there are future beings, will never see what we have seen. They will never watch the corona bloom around the black circle of the moon, never experience the strange twilight of totality, never feel the temperature drop and see the stars emerge in the middle of the day. That experience belongs to this window of time, this cosmic moment in which we happen to exist. We are lucky. We are unimaginably, improbably lucky, not just to witness eclipses, but to exist at all. The chain of events that led to this moment, to you listening to these words and me speaking them, stretches back through billions of years of contingency and catastrophe. If Theia had not existed, if she had not grown in the Lagrange point, if her orbit had not destabilized at precisely the right time, if the angle of impact had been different by a few degrees, everything would have changed. The moon might not have formed, or might have formed differently. The Earth might have been left spinning too fast, or wobbling too wildly, or stripped of the material that would become its crust. Life might never have emerged, or might have emerged and been extinguished, or might have evolved along paths so different that nothing like us would ever have appeared. But Theia did exist. She did collide with the proto-Earth. The moon did form. And here we are, 4.5 billion years later, able to reconstruct the story from the evidence she left behind. The evidence is everywhere, once you know how to look. It is in the grey dust of the lunar surface, sampled by astronauts and analysed in laboratories on Earth. It is in the seismic waves that reveal continent-sized anomalies at the base of the mantle, the buried remains of Theia's iron-rich heart. It is in the oxygen isotopes that link lunar rocks to terrestrial rocks, proving a common origin in the fires of the giant impact. It is in the anorthosite highlands, the frozen froth of the magma ocean, and in the dark Maria, the volcanic blood that filled the wounds of ancient bombardment. It is in the very fact that the Earth has seasons, that our axial tilt remains stable, that the climate has been gentle enough for long enough that evolution could produce minds capable of asking these questions. Theia gave us all of this. She gave us the moon, which stabilized our axis and gave us tides and gave us eclipses and gave us something beautiful to look at in the night sky. She gave us a larger iron core, which strengthened our magnetic field and helped protect the surface from solar radiation. She may have given us the very conditions that made complex life possible, though that connection remains speculative, a hypothesis rather than a certainty. What is certain is that Theia is still with us. She is above us in the moon that rises tonight. She is below us in the deep earth, in the structures that seismologists have mapped at the core mantle boundary. She is, in some sense, part of us, because we are made of atoms that were forged in ancient stars and assembled into planets that collided and merged to form the world on which we evolved. The calcium in your bones, the iron in your blood, the oxygen you are breathing right now, all of it was present in the solar nebula 4.5 billion years ago. All of it was sorted and processed and recombined by the giant impact. All of it carries the signature of that primordial violence. You are made of moon stuff. You are made of Theia stuff. You are made of stars and collisions and the debris of destroyed worlds. This is not a metaphor. This is physics. This is chemistry. This is the traceable, measurable, scientifically verifiable history of the atoms in your body. When you look up at the moon, you are looking at a mirror, a reflection of your own origins, a reminder that you and it came from the same catastrophe. The moon does not know this. The moon does not know anything. It is a ball of rock and dust, airless and lifeless, incapable of thought or awareness or wonder. Whatever consciousness exists in the Earth-Moon system exists only here, on this planet, in the minds of creatures who evolved the capacity to ask questions and seek answers. We are the part of the universe that has learned to understand itself, the matter that has become aware of its own history. The moon provides the evidence. We provide the understanding. And so we look up, as humans have always looked up, and we see something different now than our ancestors saw. They saw a goddess, a god, a lantern, a face, a rabbit, a mystery. We see a world, a history, a story written in craters and maria and the subtle chemistry of ancient rocks. We see the scar of a collision, the child of a catastrophe, the companion that has been with us since before we were us. The moon will continue to recede. The earth will continue to slow. The sun will continue to age, burning through its hydrogen fuel, growing brighter and hotter until, in 1 billion years or so, the oceans begin to evaporate and the conditions that support life become untenable. In 5 billion years, the sun will swell into a red giant, its outer layers expanding to engulf Mercury and Venus, and possibly the Earth itself. The moon will not survive. Nothing we have built will survive. The story we have told tonight, the story of Theia and the giant impact and the formation of the moon, will be erased along with everything else, unless some descendant of ours carries it to the stars. But that is the far future, and we live in the present. Tonight, the moon is still there. It is still close enough to raise tides and stabilize our axis and appear exactly the same size as the sun. It is still bright enough to cast shadows, still beautiful enough to inspire poetry, still mysterious enough to reward scientific investigation. It is still the same moon that our ancestors watched, the same moon that the dinosaurs watched, the same moon that has been watching Earth since the day it was born in fire. Look up, find it if you can. Let your eyes adjust to its light and notice the dark patches that form the face some call the man in the moon. Those patches are the maria, ancient seas of frozen lava, scars from a bombardment that ended before complex life began. The bright regions around them are the highlands, the original crust, an orthosite rock that crystallized from the magma ocean when the moon was young. You are looking at 4 billion years of history, preserved in stone, visible to the naked eye from 250,000 miles away. You are looking at a scar. You are looking at a tombstone. You are looking at your own origin. And if the night is clear and the moon is bright, take a moment to consider the planet that died so that you could live. Theia has no grave marker, no monument, no memorial. She exists only in the evidence she left behind, in the moon and the LLVPS and the isotopic signatures that scientists have learned to read. But she deserves to be remembered. She was a world once. She had a core and a mantle, and perhaps the beginnings of a crust. In another history, she might have become a planet like Mars, a world with its own story, its own evolution, perhaps its own life. Instead, she became us. Thank you for listening. If this story has meant something to you, I would be grateful if you shared it with someone who might also find meaning in it. There are more stories waiting to be told, more mysteries to explore, more wonders to discover in the universe that made us. Subscribe if you want to hear them. And the next time you look up at the moon, remember what you now know. You are looking at a piece of Theia. You are looking at the reason you exist. Good night.